And actually, this property or this cluster criterion is used by one of probably the first bottom-up subspace clustering algorithm, which is called CLIQUE. It uses a density-based or density grid-based cluster model, exactly the same as we had on the previous slide. So the clusters are dense regions in the feature space. The input parameter is now xi instead of s, so we partition the feature space into xi equally sized parts in each dimension. Yeah. So for example, we spend 10 partitions, 10 intervals in each dimension, in each feature, and a unit is the intersection of one interval from each dimension. Yeah. And a unit U is dense if it contains more than tau objects. So tau is our m from the previous slide here. Yeah. So S is the side length, psi is the number of partitions, and tau is now this m, the minimum number of points I want to see in one of the units in order to call this unit a dense unit. Okay, and then clusters are maximal sets of connected dense units. So there may be a dense unit finding a connected or neighboring dense unit, and I can merge them to form bigger clusters. And you see that in this case, depending on the granularity of the grid and the size of the grid and the positioning of the grid, these grid-based clustering approaches can find patterns that are arbitrarily shaped. Yeah? Similar to dbScan, but of course a little bit coarser typically. Yeah. So anyway, CLIQUE follows a two-step approach. The first step is subspace search. We'll have a look right away. And the second step is then the clustering. Yeah? So the first step is finding subspaces, and CLIQUE uses these dense units to do that. So we already explored that dense units implement the downward closure property, so we can use an a priori style search. Actually, so there's a kind of side remark here. This paper is authored by the same authors of the a priori algorithm, and some people claimed that these authors just wanted to sell their a priori algorithm for another cool or not so cool problem. But anyway, it's one of the pioneering subspace clustering algorithms anyway. Yeah? So they explore the downward closure property of dense grid cells in order to compute all subspaces having dense grid cells. And well, the most interesting part is the candidate generation, which is exactly the same as in the a priori frequent item set mining algorithm. It is based on the set of k-1 dimensional dense units, which is denoted as dk-1. From those dense units of dimension k-1, we generate a candidate set of dimension k by self-joining all subspaces in dk-1, and the join condition is exactly the same as in the frequent item set mining problem, that the units have to share the first k-2 dimensions. Yeah? And you can show that this is actually a complete join, or the candidate set you generate with this join condition is a superset of all dense grid cells of dimension k. Yeah, we can then of course discard those candidates which have a k-1 projection that is not included in dk-1, which may happen. Also, we use this join condition here, the same as in frequent item set mining, and only for the remaining candidates we have to check the density, because still they are candidates and we have to check them. Yeah? So we basically search for dense grid cells instead of item sets that follow or that have a minimum support. So having all the dense grid cells, in the second step we want to find, or CLIQUE finds clusters as the maximum sets or the maximal sets of connected dense units. So given a set of dense units in the same k-dimensional subspace, this second step outputs a partition of D into k clusters of connected dense units. So we need to find those dense units that are connected, and the authors propose to represent this problem as finding connected components in a graph where the nodes are the dense units and the edges between two dense units are the or there is an edge if those two nodes have a common face, so they are neighboring actually, and then they use a depth first search algorithm to find those connected components in this graph here. Yeah, so that's it. Short discussion on that. So we have basically two input parameters, xi and tau, which specify the density threshold. It outputs all clusters in all subspaces. Clusters, of course, may overlap. It is a very simple but quite efficient cluster model, which is true also for the non-subspace version of grid-based clustering, of course. However, the whole thing has some downsides. It's basically related to the fact that it uses the fixed density threshold for all subspaces, because this ensures the downward closure property. If we change the density threshold, so this xi and the tau along the subspaces, then we won't have the downward closure property anymore, and we cannot apply branch and bound. So we use a fixed, or CLIQUE uses a fixed density threshold, and it's just for performance reasons in order to apply a priori style branch and bound search, bottom-up search. So what are the problems with this fixed density threshold? Well, in fact, to represent a cluster in 10D, a 10-dimensional unit must contain as many points as in 2 dimensions. So, and of course, you know from the cursive dimensionality that the probability, so I mean, you always have n points, and of course the probability that a given number of n points is in a 2-dimensional grid cell, or is in a grid cell in a given window, rectangular window, in 2D is much higher than in 10D. But you apply the same density threshold in any dimensions, and that of course is somehow arbitrary. So if you set the density threshold too loose, you may end up in quite high dimensional feature spaces, but then in 2 dimension, in the 2-dimensional case, virtually everything, all units are dense actually, just because of the cursive dimensionality thing. On the other hand, if you set the parameters very strictly, then you end up in only very small dimensional or low dimensional subspace clusters. But on the other hand, that might be much more efficient, because then the branch and bound search stops much earlier than the other way around. So that is a kind of trade-off between getting more clusters and higher dimensional clusters versus getting clusters in a reasonable time actually. So scalability versus potentially accuracy, but you never know if you want to have 2-dimensional clusters or 10-dimensional clusters. Anyway, so second point, for a cluster C in subspace S, all clusters in all projections of S are of course also reported as clusters because they are also dense. So we have an extremely high redundancy in the results. So if I have, for example, this one here as a cluster reported, I also get this, and this one reported as clusters, and also of course the 1-dimensional units, this one here, and this one here reported, so this one, sorry, this one here along the z-axis, and this one here along the y-axis. So for this 3-dimensional cluster, which is 1, I get another 1, 2, 3, 4, 5, 6 redundant clusters that basically have the same information. I mean, the lower dimensional projections, of course, have potentially more points than the three-dimensional stuff here, but it is more or less the same information, and I get that in a very redundant way. Yeah. So there's another downside. And that third thing follows from the second thing. Which of the redundant information is more interesting? Is it the higher dimensional one, or is it the lower dimensional one, which may contain more points or even units? Yeah, what is more interesting? What is more specific? What is more generic? You never know. And since it's unsupervised, it's hard also to somehow judge it or to measure that. Yeah. So yeah, that is and all those problems actually follow from this fixed density threshold. Yeah, and still the worst case runtime is of course still exponential in the number of dimensions, like any branching bound bottom-up search here in this 2 to the power of d search space. Yeah, so worst case runtime is still exponential.